Hi, we're starting our unit on solutions today. And this introduction kind of runs you through what solutions is, a lot of sort of background information, things that we've already learned as we switch from learning about gases to learning about solutions. We've covered some of this before, and we're going to get into right now. Today, what is a solution? How do they work? What are some terms and definitions that would go along with that? So you may remember when we were classifying mixtures, they could either be homogeneous or heterogeneous. This part is kind of a review. Feel free to write it down if you want. Heterogeneous, meaning that the particles were not evenly mixed or unevenly mixed. Think like a salad or, I don't know, something with chunks in it. And then homogeneous would be the particles are uniformly mixed. Think like a Gatorade or something like that, that were like the same taste every time. There's a picture of homogeneous and heterogeneous and what they might look like. The idea is that a mixture, though, is a thing that is physically combined. So you can uncombine a mixture. Uncombine, aka separate a mixture by physical means, because you're just putting two things physically together. You may also remember when we did homogeneous and heterogeneous mixtures, these were under the umbrella of matter. On one side we have pure substances, the other side we have mixtures, and then we had homogeneous and heterogeneous. And now we're going to add some definitions, the bottom three here, solutions, colloids, and suspensions, to them. So solutions are homogeneous mixtures of two or more substances, and they're uniform to one phase. So a solution could be like Gatorade, or it could be like, I don't know, Diet Coke. Excuse me. But the idea is that it's one phase. Solutions don't always have to be a solid dissolved in a liquid. They could be liquids dissolved in liquid, like a mixture of like isopropyl alcohol you might buy at Target. That's some alcohol and some water mixed together, but it appears to be as one thing. Or even solids, gases dissolved in solids, or even other solids dissolved in solids. You just melt them down and mix them together. Steel is an example of a solution, which we call an alloy. When it's two solids mixed together, but they're melted first and then mixed together. So salt water is a good example of a solution as well. Colloids are sort of the in-between solutions and suspensions. A colloid is a mixture that appears to be homogeneous, but not at a molecular level. So when you are examining it, it looks like it's one thing, but if you took a microscope to a colloid, you'd notice that the particles are not actually evenly distributed. But from far away, it looks like it is. The only example I think that I'll use for this unit would be milk. So if you sort of step back and look at milk, it looks like one uniform thing. But if you were to take a microscope to it, milk is just fat particles suspended in water, and those fat particles look the same from far away. But if you got close enough, you would notice that they're actually not all the same size, and so it is called a colloid for that reason. Probably lots of things are colloids. If you took a microscope to many things, you might notice in the colloids, maybe even something like as simple as like your coffee. If you like took a microscope to it, you would notice that there's different oils dispersed throughout. It's not exactly uniform, but for the purposes of this class, our big example will be milk. And then a suspension is a mixture in which big particles will settle out after stirring. So think like muddy water. When you stir it up, it looks like one thing, but if you let it sit for a while, the big particles will settle to the bottom, and it'll be very clear that it's not one uniform thing. Okay, so those are the three, and the major difference between the three of them is particle size. Particle size is what separates a homogeneous solution from a heterogeneous one, like a suspension or a colloid. As the particles get bigger and bigger, then you're most likely dealing with a colloid or a suspension. Solutions themselves contain two types of substances. So again, a solution is a homogeneous mixture of two or more substances, and they appear to be in one phase. Usually for us, that's the liquid phase. And they have to contain two types of substances. The first thing is the thing that does the dissolving. We call it the solvent. Most things that we deal with the solvent is water. Water is sometimes called the universal solvent because it can dissolve lots and lots of things. But that is the thing that's maybe you'd say that's the major ingredient. Like when you dissolve salt in water, there's plenty of water and just a little bit of salt. So solvent is the water. That's the thing that does the dissolving. Again, if the solvent is water, since it's so common, we actually have a name for those. Those are called aqueous solutions. I mean, you've seen that word before. So if the thing is dissolved in water, like many, many things are, we call those aqueous solutions. And the thing that's getting dissolved, the thing that's being dissolved in the solvent, we call that the solute. It's the minor ingredient. Like if we're talking about salt water, then water would be the solvent and salt would be the solute. So again, those are the particles that are dissolved in the major solvent. You can have lots of other ones, as I mentioned too, solid gas mixtures as well. I already talked about steel a little bit, chrome, a lot of alloys, which are just solid solutions. Alloys like chrome, brass, bronze, those things are pretty common, but you'll notice that those things are not on the periodic table, even though you've heard those words before. There's no spot for steel on the periodic table because steel is a mixture of like iron and nickel and a few other things. But it's all melted down and then mixed together. And when it cools, it looks like it's one thing. And that is what we call a solution. But a solid solution has a special name. We call it an alloy. Anyway, no matter. In this class, most of the solutions will be aqueous solutions, but you can have lots of mixtures as well. Even dissolving carbon dioxide in your Celsius drink that's so good. That's still a solution. There's a gas dissolved in the water. Oh, there's some arrows that are just popping up here for funsies. Don't know why. You can separate mixtures all sorts of ways. Some of the popular ones are if it's like muddy water and you let the mud settle to the bottom, you can just decant that, which means you just pour off the water and the mud sits at the bottom. Another way to do that same kind of idea is called centrifuge. If you spin it really fast, all the mud settles to the bottom, and then you pull it out of its little centrifuge, and you can just pour the water off real easily. Evaporation is another way to separate mixtures. When you evaporate, like let's say salt water, or even just like sugar in your Gatorade, when you evaporate the Gatorade, all you're evaporating is the water. The stuff that's dissolved in there will not evaporate. And so if you evaporate, like let's say salt water, when it's all said and done, there's going to be a bunch of actual crystallized salt in your container, and the water will be all gone. That's another way to separate mixtures. You can do that faster by boiling it. If you guys have ever made rock candy, that's how rock candy is made. When you evaporate things very slowly, the crystals have a long time to form, and it's just a solution of sugar water. And as the water evaporates, the sugar forms these giant crystals, and then eventually all the water is gone, and then all you have is a bunch of sugar left over. Another way is like boiling, condensation. We just kind of mentioned that when you boil it, it's just a faster way to evaporate something. Boiling condensation's kind of like a, what's that called? A evaporation funnel in a chem lab, which I'll get a chance to show you at a later date. Chromatography, paper column chromatography, that's just when you take a liquid to a mixture of liquids, and then you let them go up a piece of paper. And then some of the liquids like paper and some of the liquids don't like paper, and so they travel at different paces, and you can separate them that way, which is a thing that we'll end up doing in this class. All right, so again, another important property of how to make a solution is solubility. You might remember solubility just measures how well one thing dissolves in something else. Usually it's how well the solute dissolves in the solvent, if we could use our brand new words we just learned. So, and this will kind of be a throwback for some things we learned right at the beginning of the semester, but there's two types of compounds, polar and nonpolar. Polar compounds on paper, their Lewis structures are not symmetrical, and nonpolar compounds, the Lewis structures are symmetrical. You might remember intermolecular forces where we learned about these things. Well, one thing that's important is that polar compounds will dissolve other polar compounds. This is why water, which is very polar, dissolves things that are also pretty polar. If you use water to clean up let's say grease stain on your pans, just by itself, water is not going to get the job done because water is polar and grease, like oil, is non-polar. So it won't work. But if you were using something else to dissolve that grease, that might work. And so and that's where nonpolar compounds dissolve other nonpolar compounds. So when you take that pair of greasy pans, because you can't like eat a piece of pizza without like just slapping it face down on your pans. When you take that pair of pans to like a dry cleaner, they don't use water to clean it off. They use a different compound. Usually it's carbon tetrachloride, but carbon tetrachloride is a nonpolar compound. And so a nonpolar compound very easily cleans up the nonpolar grease from your pants. Of course, the other way to do that is to use a soap, right? That's what we would use at home. You'd use a detergent and put the pants into our washing machine. While a soap is just a giant long chain molecule where one side has a polar piece and the other side has a nonpolar piece. And so soaps just allow water to interact with nonpolar molecules. So that's how we solve that problem at home. But if you were going to a dry cleaner, they would just use a nonpolar compound. So instead of saying, polar dissolves nonpolar or polar dissolves polar or nonpolar dissolves nonpolar, we usually just say like dissolves like. If I told you that, for example, water was polar and water didn't dissolve grease, then you could assume that grease would be nonpolar because we know that like dissolves like. Another couple words that go along with it, something that's miscible means it is able to be mixed or dissolved. And then if it is immiscible, it means that it does not mix or does not dissolve. So there are certain things that are immiscible because they don't dissolve in water very easily. And then things that do dissolve in water and very easily, we call them miscible. Oh, fun. You will have a homework quiz, and these are the questions that go along with it. And you can start them right now, right away, on page 459, numbers 1 through 6, 9, and 12, and anything that I failed to cover in this delightful little talk, you could just flip back in the pages in the book and find the answers to those questions. It's pretty convenient to have a book on an iPad in the year 2022. Anyway, this has been super fun. Hope everyone's doing great. I'll see you soon. Okay, bye. Oh, there's a picture. Bye.